And welcome back, everybody. So this is our first video lecture on unconfined aquifers and how we use well tests data to find the properties of an unconfined aquifer. So for unconfined aquifer, and you have a visual here on the right that tells you what the Wells function will look like. So you can see there is yet a new family of curves on the right hand side here that we didn't have before. So a few assumptions first. So the aquifer, of course, is unconfined. The vadose zone has no influence on the drawdown, so meaning the soil, or we're only talking about the saturated aquifer, the proper unconfined aquifer. Now the water is initially pumped from instantaneous release or from a confined-like behavior. So again, the compressibility of the water and the skeleton. So when you start the pump originally, right, you get that shock, and really it's like almost as if storativity was providing the water, right? Now after a while, gravity starts feeding water, right, from vertically, right? It's just like the leaky confined aquifer. We have water starting to flow down, but now gravity is actually feeding that water. So there's a period where it looks like a semi-confined or leaky confined aquifer, where there is an equilibrium almost between the pumping and basically the gravity or the water table dropping, or just gravity feeding water to the well. Now at some point a little bit later, the limit is reached when the specific yield, right? So there's only so much water that gravity can feed the well. And that limit, or this amount, is limited by the specific yield, right? So if the specific yield is 15 or 20%, that's the most water you can get per time. So now we're starting to have a behavior that is like a confined aquifer again, right? So on the what we call the B-type curve, on the right-hand side here, now we're starting to follow a Theus curve again, like a Theus curve here and a Theus curve here. A-type curve, Theus B-type curve here. So we're starting to follow a Theus curve again, the same behavior, but except now instead of the storativity, it is the specific yield, that is providing that behavior. So therefore, if we have data again, and we can fit the left-hand side and then the right-hand side, now we can actually find what the specific yield is. Oh yeah, the aquifer can be anisotropic, that's fine. So here is the equation. So again, this is the same equation as before, but now our Wells function has 3 parameters instead of 2 for the semi-confined or 1 for the confined. And that, so now we have UA, UB, and gamma here. So this gamma here is given here, and this is the ratio. So now gamma is different from that R over B that we had for the semi-confined aquifer, right? So gamma now gives us information on the ratio of vertical versus horizontal hydraulic conductivity. So think of an anisotropic aquifer where KV and KH are different. Excuse me, that should be obviously K horizontal, K vertical. Right, so if it's anisotropic, depending on the ratio, you get more water from the horizontal sheet than from the vertical, just because of the hydraulic conductivity ratio. So that gamma again gives us a little bit different, information, if you will. Again, you would need to know the aquifer depth in order to get the horizontal aquifer hydraulic conductivity, excuse me. In order to get the horizontal hydraulic conductivity, you will need to know the aquifer depth. The UA, so the first parameter, gives us, just like before, the storativity and transmissivity. So transmissivity and storativity as if the aquifer were confined, again, on the left-hand side. And then UB is where the new things arises, right? So this is now a function of the specific yield. So once we fit the right-hand side, the B-type curve, we'll be able to get the specific yield out of this data. Again, type A curve, type B curve, you know, those are Thies curves basically on the top and bottom. I already went through that. And now we have 3 parameters. So UA is just the confined type A, UB is the confined type B, and then this gamma is that family of curves here, given here. So 3 things we can read. Now here's an example where data is fitted to the left-hand side, so match the type A curve just like before. So this is the process, right? And I'll show you in Excel again. I'll do a tutorial with that Excel interface that we have for this unconfined case. But match the type A curve first, and now we can read gamma and UA, so we can get the storativity, the transmissivity, as well as which family of curves we're on. Once we have that, gamma gives us the ratio of KV and KH. And again, you need to know B, so you can get KH. Then finally, we go read the type B curves, right here. The type B curve, so we switch the data to the right-hand side, read the type B curve, and now we get UB, so we can know the specific yield for an unconfined aquifer. Okay, I will stop here. So that was all the conceptual introduction on unconfined, that B-type curve, basically, and I will post a short video tutorial again on the Excel interface where we will treat this example that I just showed, but with the Excel interface, so you can follow along there how to do it. Thank you.